Is it visible? Can you
Yes,
see
sir.
the
Yes.
presentation?
Yes, sir. Yes.
Okay.
Yes,
Okay,
sir.
there was some problem. They were reporting some problem, Google Meet. Anyway, so here the expression for the Z transform, if you absorb tau within A, it is given by this expression. That is the expression for the Z transform. So in this case, the ROC, that will be the magnitude of e to the power minus A. You draw a circle with center at origin in the Z plane, circle with radius, magnitude of e to the power minus A. So ROC is the entire outside of this circle or exterior of this circle. All right. So those are the Z transforms that we considered. We also considered the impulse sequence or Kronecker delta sequence or unit sample sequence. There the Z transform was 1, and the entire Z plane was the region of convergence. Region of convergence means the region in the Z plane where the Z transform will exist. In other words, the region in the Z plane where the magnitude of xz will be finite. Now have a look at the causal sinusoidal sequence. Xn equal to 0 for n less than 0, and it's a sine omega 0 n tau for n greater than equal to 0. Incidentally, in the earlier case, I have considered the ROC as magnitude of e to the power minus a. If instead of the sequence I had considered the sequence e to the power minus a n tau, what would have been the ROC? Magnitude of z greater than e to the power magnitude of e to the power minus a tau. Then the radius of this circle will be magnitude of e to the power minus a tau. All right, tau will be there. Now consider the causal sinusoidal sequence. Causal sinusoidal sequence means that the sequence has zero values, identically zero values for n less than 0. And for n greater than equal to 0, it has a expression a sine omega 0 n tau. I have shown only one complete cycle of this discrete time sine wave. There will be infinite number of such cycles extending up to n equal to infinity. What will be the Z transform? How will you obtain the Z transform of this sequence? First of all, start from the basic expression, or you may say that you may split it up into complex exponentials, isn't it? The sine function. And then use your knowledge of the earlier Z transform to obtain the expression for the Z transform of those exponential functions. Then you merge them together and obtain the Z transform for this causal sinusoidal sequence. You've drawn it. So this is the expression. So it's a causal sequence. So the summation starts from n equal to 0 to infinity. That is the expression. You are splitting up the sinusoidal sequence into exponential, in terms of exponential sequences. 2j is there in the, yes. Those summations you have already evaluated, those summations. Or it simply follows from this expression that this summation will be 1 by 1 minus e to the power j omega 0 tau z to the power minus 1. And that one will be 1 minus e to the power minus j omega 0 tau z to the power minus 1. Now remember that each of this, under what condition will that summation, converge to this expression? It will converge to this expression provided that magnitude of z is greater than magnitude of e to the power j omega 0 tau, isn't it? Magnitude of z is greater than magnitude of e to the power j omega 0 tau. That means magnitude of z is greater than 1, because magnitude of e to the power j omega 0 tau is 1. Here also, the condition for that summation to converge to this expression is that it should happen if magnitude of z is greater than e to the power, magnitude of e to the power minus j omega 0 tau. That is also 1. So magnitude of z is greater than 1 for both these cases. So you simplify it further and obtain that expression, and ROC is magnitude of z greater than 1. You write down these expressions, then I'll proceed. In the course of writing down this expression, please also check whether there is any error or not.
Hello, sir.
Yes.
Sir, in the case when mod z is less than 1, then in that case we will not get finite value of z transform.
That is true. So that's why I'm saying that the ROC is magnitude of z greater than 1. So with every z transform, you have to write down the region of convergence. Say, if you will see later that if you treat the case of inverse z transformation, that means for a given xz, if you want to get back the original sequence, time domain sequence xn, in absence of knowledge of the ROC of xz, you cannot do that uniquely. There will be ambiguity. Have you written these expressions?
Yes, sir, done.
Yes, it does.
So ultimately, the z transform is given by that expression. That one and also this one, same. So ROC is magnitude of z greater than 1. I have explained why the ROC is magnitude of z greater than 1. Because that is the common ROC of each of these expressions, summations, each of these summations. What do you think? Where will the poles be located? Poles of the Z transform? Now, there is a misconception that we are interested in the poles only in case of systems, the location of the poles. That's not true. For signals also, the poles have significances. The poles of the transforms, I mean. So where will the poles be located? For that, you have to factorize this denominator. If you factorize this denominator, you will get an expression of this form. Z minus e to the power j omega 0 tau times z minus e to the power minus j omega 0 tau. It implies that you have a complex conjugate pair of poles as expected, because in case of a continuous time causal signal also, the Laplace transform had a pair of complex conjugate poles. So here in this case, where will the poles be located? The magnitude of the poles, each of the poles, the magnitude is 1. And argument is omega 0 tau here and minus omega 0 tau there. So 1 e to the power plus minus j omega 0 tau. So those are the locations of the complex conjugate pair of poles. All right. These are the poles. The poles lie on the unit circle. Recall that in case of the continuous time sinusoidal signal, what happened? The poles, they were lying on the j omega axis. The Laplace transform poles, they were on the j omega axis. And here it's they are on the unit circle centered at origin in the z plane, the circumference of the unit circle. They lie on the circumference. And these angles are, this is omega 0 tau, this is minus omega 0 tau. All right. You can easily understand that for a given tau or given sampling frequency, larger is the value of the frequency of the sinusoid, what will happen? The poles will shift in this direction. All right. The poles will shift in this direction. The spread will become larger. Now here also, as in the case of the exponential signal, here also you may absorb, you may consider the sequence as a sine omega 0 n un. All right. A sine omega 0 n un. It implies that tau has been absorbed within omega 0, because I have pointed out at the beginning that once the time period is fixed to the processor, these samples, they are nothing but a sequence of numbers. Thus, tau doesn't have any significance as such. So tau can be absorbed within the angular frequency. If tau is absorbed within the angular frequency, what will be the unit of the angular frequency? Instead of radians per second, it's radians. So that happens only for discrete time signals. So if it is a sine omega 0 n un, omega 0 is in radians. Then the poles will be located at, where will be the location of the poles? 1 e to the power plus minus j omega 0. This will be the location of the poles. Instead of omega 0 tau, it will be omega 0. Let me see whether I have used a different symbol for omega 0, because there the angular frequency is in radians. Yes, I have used capital omega here. So in case of discrete time filters, etc., discrete time systems, you will find often that when you are given to design, when you are given the task of designing a filter or something like that, then often what is done is that the cutoff frequencies, they are expressed in radians instead of radians per second. Can also be that is missing. So remember that in this case, A sine omega 0, capital omega 0, n un, the Z transform poles will be simply as shown here, but that angle will be capital omega 0 and this is minus capital omega 0. If I ask you to derive expressions for the Z transforms of causal sinusoid or causal cosinusoid, whose amplitude is exponentially decaying or exponentially rising, can you do that? The task is very simple. You split up the cosine or sine function in terms of complex exponential, combine them with e to the power minus an or whatever it may be, and then proceed. So this is left as an assignment, as a task for you, that you obtain the expressions for the Z transforms of A cosine omega 0 n un in the same line as I have mentioned, and I have given you the answer here. So ROC here is magnitude of Z greater than 1. So these are expressions for sine waves, sinusoidal sequences modulated by exponential sequence, because it's multiplied by e to the power minus an. So here we have, if a is a real number and it's greater than 0, what will happen? That will represent a sine wave whose amplitude is progressively decreasing, a decaying sine wave. And here, under similar conditions, it will be a decaying cosine wave. In both these cases, the ROC will be magnitude of Z greater than magnitude of e to the power minus a. Now have a look at the properties of Z transform. First property is obviously, like other integral, like other transforms, it's the property of linearity. If capital Fz is the Z transform of the sequence Fn and capital phi Z is the Z transform of the sequence small phi n, and alpha and beta, these are constants, then if you have a sequence Xn, which is a weighted linear combination of Fn and phi n, as shown here, then Xz will be alpha capital Fz plus beta capital phi Z. So that is the property of linearity.
Sir, what will be the ROC of the combined signal?
ROC of the combined signal will be at least the intersection of the ROCs of the individual sequences. At least the intersection of the ROCs of the individual sequences. ROCs of the individual Z transforms. That means at least the intersection of the ROCs of Fz and phi Z. Intersection obviously means the common, the overlap. You have written it.
Yes, sir.
Multiplication by a to the power n, it will have an effect of multiplication of the sequence under consideration by a to the power n. So that will have an effect of scaling in the z domain. Say we have the z transform of a sequence xn represented by xz, and say its ROC is magnitude of z greater than R2 less than R1. Now, why have I considered that type of an ROC? Because you will find later that all ROCs are of that form. Under special cases, say take the case of the Z transform of unit step sequence. All right. In that case, what will happen? In that case, if you express the ROC in this form, R2 will be unity and R1 will be infinite value. So all ROCs you will find later that they can be expressed in that form. R2 and R1, they can take on values of, R2 can take on values of from 0 to something, some finite value, and R1 can take on values of some finite value to plus infinity. Now here I have given the proof of this property. Start from the basic expression for the Z transform. Z transform of a to the power n xn. So that is the basic expression for the bilateral Z transform. A to the power n xn times z to the power minus n. Now here you club a to the power n and z to the power minus n together. So you can express it as a to the power minus 1 into z, that product raised to the power minus n. Now if it were summation xn z to the power minus n, it would have been xz. But here in place of z, you have a to the power minus 1 into z. So it is xz with z replaced by a to the power minus 1 into z. Proof is quite simple. Say z, the z transform of half to the power n un. Here a is half. So it will be according to what I have written. What is the z transform of un? 1 by 1 minus z to the power minus 1. In that expression, replace z with half to the power minus 1 into z. So it will become 1 minus half z to the power minus 1. Now have a look at an important property, which is the real translation property or shifting property.
Sir, sir,
Yes.
in the exam, if we are asked to derive the Z transform of exponentially decaying discrete sinusoidal sequence, then we have to use the basic definition of Z transform, or we can do this via the multiplication by a to the power n, that is scaling in Z domain property.
It depends how the question is framed. If you are asked to derive it from the first principles, or the language is such that starting from the basic expression for Z transform, derive it, you have to start from the basic expression.
Okay, sir.
Derive from the first principles also means deriving it from the basic expression for Z transform. If nothing is mentioned, you can use the property.
Okay,
All
sir.
right.
Thank you.
Now coming to the shifting property, say if xz is the Z transform of the sequence xn and capital K is a positive integer, then Z transform of the sequence xn minus k will be Z to the power minus k into xz. All right. If k is a positive integer, what is this sequence xn minus k? It is the sequence xn shifted right by k samples. Xn shifted right by k samples. All right. That means xn delayed by k samples. The delayed version of xn. Or if you consider xn tau or x at t, it will represent x at t delayed by k tau units of time. K tau units of time. Delaying by k sample means delaying it in terms of time units, k tau units of time. What will be z xn plus k? It will be z to the power k xz. In this case, ROC will be same as xz except z equal to 0. Why? Because here xz is getting multiplied by z to the power minus k. That means 1 by z to the power k. All right, where k is a positive integer. Therefore, because there is the term 1 by z to the power k, at z equal to 0, that z to the power minus k into xz, its magnitude will become infinite. So z equal to 0 has to be excluded. It cannot be there in the ROC. Similarly, z to the power n plus k, it will be z to the power k xz. ROC will be same as xz except for z equal to infinity. Just the reverse thing will happen here. If you substitute z equal to, as z tends to infinity, what will happen to z to the power k? It will become infinite. That expression will become infinite. So z equal to infinity has to be excluded from the ROC. It means that magnitude of a z transform by z to the power minus k has the effect of delaying the time function x at t by k tau samples or delaying the sequence xn by k samples. Multiplication of the z transform by z to the power k, where k is a positive integer, has the effect of delaying the time function x at t, advancing in time the signal x at t by k tau units of time, or shifting the sequence xn to the right, to the left by k samples. Remember, this is the reason. So if k is equal to 1, then z to the power minus 1, it represents a unit, what is called a unit delay. It represents the z transform of a unit delay. That is the reason why in most of the cases, when I am considering the rational z transform expression, ratio of polynomials in z, instead of writing it down in terms of ratio of polynomials in z, I am writing it as a polynomial in z to the power minus 1. Unit delay has a very important implication in DSP. We'll come to that later when we discuss about the systems. Multiplying by z to the power minus k is delaying in time domain. So it's called, the first one is called right shift or backward time shift property. The second one is called left shift or forward time shift property. Next property is the real convolution property. In DSP, you have this real convolution, you also have circular or periodic convolution. That type of convolution will be dealt with in the other part of the syllabus. So here we are considering real convolution property. You can easily guess what is this property. If you have convolution in the time domain, correspondingly you will have a multiplication in the z domain. First of all, let us see, we have studied convolution in connection with continuous time signals. But what will happen in case of discrete time signals? In case of discrete time signals, because in case of continuous time signals, you have that convolution integral. In case of what is the discrete time counterpart, it's summation. So convolution will be obtained by a summation expression. Discrete time linear convolution or convolution sum of two sequences xn and gn. This is the expression. Same sign for the convolution operator. So summation over k equal to minus infinity to plus infinity xk gn minus k. K is a dummy variable. It doesn't appear in the final result. So how will you proceed? Consider n equal to 0. Evaluate this summation for n equal to 0. You get y0. Consider n equal to 1. Evaluate this summation for n equal to 1. You get y1. Consider n equal to minus 1. Evaluate this summation for n equal to minus 1. You will get y minus 1. In this way, you have to proceed. Now, if yz is the z transform of the sequence yn, xz is the z transform of the sequence xn, and gz is the z transform of the sequence gn, then according to this property, yz will be the product of xz and gz. ROC will be at least the intersection of those for xz and gz. The proof is also there. These are the z transforms of yn, xn, and gn respectively. Now in the proof, I have started from the basic expression for the z transform of yn. So this is the expression. And in this case, yn is the convolution of xn with gn. So yn has been substituted by the convolution sum expression. This one within brackets is the convolution sum expression representing yn. I rearrange the terms, say xk and has been brought to the left. I just interchange the order of summation. K equal to minus infinity to plus infinity xk times that summation. All right. Now, if you multiply, if you introduce here z to the power minus k, what will appear there? Z to the power plus k will appear here. So in effect, the second summation becomes gn minus k z to the power minus n minus k. All right. So the first summation represents xz and the second summation represents, what is that? Gz. So it's xz times dz. So don't make a mistake. If it were gn minus k z to the power minus n, it would have been the z transform of gn minus k. But here it's not like that. Gn minus k here and z to the power minus of the same thing. So if you can simply write, replace n minus k with m. So here you will have gm z to the power minus m. And summation will be there from m equal to minus infinity to m equal to plus infinity.
Answer.
That's what I've done here. Now, if xn and gn, they are both causal sequences, then this summation, instead of extending from minus infinity to plus infinity, it should extend from k equal to 0 to n. The same thing you observed in case of the convolution integral, isn't it? Convolution of two continuous time signals. In the expression for the convolution integral, the integration was performed from 0 to t. Here it's 0 to n, the current sample, the current sampling instant. In case of continuous time signals, you came across energy and power signals. So here also you can have energy and power signals, the concept of energy and power signals, the counterparts. But here, first, how will you define the normalized energy? How will you define the energy of a signal or sequence? In case of the continuous time signals, it was the integration over minus t to plus t, then the magnitude of xt square that was there, and the limit was introduced that capital T tends to infinity. It's just the counterpart for discrete time signals. So it is actually summation over n equal to minus infinity to plus infinity x magnitude of xn squared. Normalized power P is given by limit capital N tending to infinity 1 by twice n plus 1 small n equal to minus n to plus n magnitude of xn squared. It's not 1 by 2n, but it's 1 by 2n plus 1. Because how many samples are involved here? Starting from minus n to plus n number of samples to the right of 0, and n number of samples to the left of 0, and small n equal to 0 itself. So 2n plus 1. So if E is finite, obviously this power will be 0. In this case, we say that the sequence under consideration or the discrete time signal under consideration is an energy signal. If E is infinite, P may be finite or infinite.
Sir, why are these called normalized energy and normalized power?
Normalized because that can be explained for continuous time signals. In the case of continuous time signals, what did we observe? That for this energy to be the energy of a signal, say the resistive load, that was considered as unity. So that's why it's called normalized. Unless you do this normalization, you cannot use this term energy or power as some attributes for signals. Without normalization, they will depend on the system to which the signals are being applied. So to have this energy and the power as properties of the signal, you must do normalization.
Okay, sir. Thank you.
In case of continuous time signal, we say that energy normalized to unit resistance and power normalized to unit resistance, like that. So colloquially, you simply use the term energy and power. It's implied that it's normalized. So when P is finite and E is infinite, then we say that Xn is a power signal. If none of these conditions is satisfied, Xn is neither an energy signal nor a power signal. Have you written it?
Yes, sir.
Now we consider the correlation property of Z transform. If you have finite energy sequences or energy sequences simply, Xn and Yn, then the cross correlation of the two, there will be two cross correlations, Rxy and Ryx. Those are the definitions. Rxy will be given by that summation Xn into Yn minus L. It will be same as summation xn plus L into yn, L having values of 0, plus minus 1, plus minus 2, etc. So that is the cross correlation of finite energy sequences. Another cross correlation will be involving these two sequences RYX. We are discussing properties of Z transform. So obviously here we are interested in pointing out what will be the Z transforms of these cross correlation expressions, because they are also sequences. They are also sequences, so they will have their own Z transforms. Now Z transform of Rxy, due to historical reasons, the Z transform of the cross correlation is represented not by capital R but usually by capital S, because you remember that the cross correlation, if you take the Fourier transform of the cross correlation of two continuous times signals, that will result in the cross power spectral density. So that is the reason. So Z transform of Rxyl, it will be the product of Z transform of X and the Z transform of Y with Z replaced by Z to the power minus 1. What will be the ROC? ROC is at least intersection of the ROCs of xz and y with argument z to the power minus 1. Now this is a property of cross correlation. It's Rxyl will be Ryx minus L. Just for noting. You know that correlation is a special case of convolution. Now, for finite energy sequences, the autocorrelation will simply be the correlation of a particular sequence with itself. So those are the expressions. Therefore, you can easily understand what will be the Z transform of the autocorrelation sequence. It will simply be the product of xz with capital X with argument z to the power minus 1. Written it?
Yes, it does.
ROC you can easily understand. It's the at least the intersection of the ROCs of xz and xz to the 1 minus 1. Next property is time multiplication property. If you multiply a sequence with n, then the z transform is minus z dxz dz, where xz is the z transform of the sequence xn. Now the z transforms of nxn and the z transform of xn, they will have the same ROC. What will the sequence n into un represent? What do you think? What does it represent?
Ramp, sir, ramp.
Ramp.
Time.
The sampled version, uniformly sampled version of a continuous time ramp. Again, consider the z transform of unit step. It's z by z minus 1. So z transform of the ramp nun, it will be minus z duz dz. Yes. So z transform of nun, it's z by z minus 1 whole square. Now let me point out something here, and also I'll also refer back to the causal sinusoidal sequence expression. Now here, what are the location of the poles? Two poles located at z equal to 1. All right. So it implies that if you have a sequence in general, if you have a sequence in general, then if that sequence has more than one pole located at z equal to 1, all right, located at z equal to 1, then that sequence, I'm talking about the causal sequence. If you have a causal sequence with a Z transform having two poles located at Z equal to 1, then that sequence, it will grow, have a component that will grow with time. All right, that is the implication, that will grow with time, because n even is a sequence that is increasing with time. Therefore, if any causal sequence, xn or gn or yn, anything, if it has maybe besides other poles, it may have more than one pole located at z equal to 1, then that will imply that the sequence has a component at least which is growing with time. All right. Now, if you refer back to that sinusoidal sequence or cosinusoidal sequence case, once you have written it, I'll move back.
Answer.
In here also, in case of sinusoidal sequence, you have found that there are both for the sinusoidal sequence as well as for the cosinusoidal sequence, there are two poles, complex conjugate pair of poles lying on the circumference of the unit circle. All right. Now, here it implies that if you have a causal sequence and that causal sequence has, besides having other poles, it has a pair of complex conjugate poles on the circumference of the unit circle centered at origin in the z plane, then that causal sequence will have a component which is a steady oscillation, which is an oscillatory in nature with steady amplitude. All right. It will have a component which is oscillatory in nature with steady amplitude. Now, from those two expressions, you have to find out what's the implication of having a complex conjugate pair of poles not lying on the circumference of the unit circle, but maybe inside the unit circle. That is one of the cases. Here, say, inside the unit circle, or a complex conjugate pair of poles outside the unit circle. What's the significance? That you have to obtain from any one of these expressions. Try that. Like other transforms, Laplace transform, here also you have an initial and final value theorems. If xz is the z transform of a causal sequence, then this is the expansion of xz. Now x0, the initial value of xz, it can be obtained without actually determining the inverse z transform. All right, it's limit z tending to infinity xz. All right, if z tends to infinity, then all these terms will vanish. Only x0 will remain. So x0 is given by limit z tending to infinity xz. That is the initial value theorem. Once you obtain x0, you can obtain x1 in this way. X tau, x1 or x tau, same thing. Limit z tending to infinity z xz minus z x0. How will you get that? Multiply both sides by z. All right. So zxz will be zx0 plus x1 plus x2 z to the power minus 1, like this, all these things. So in that case, if you introduce this condition, limit z tending to infinity zxz minus zx0, then that will be equal to x1. Just try out, multiply both sides by z. You will have here on the left hand side, you will have zxz. Here you will have zx0. You shift zx0 to that side. So you have this zxz minus zx0. What will remain on the right hand side? x1 plus x2 z to the power minus 1 plus x3 z to the power minus 2 plus x4 z to the power minus 3, etc. Therefore, on the left hand side, if you are having zxz minus zx0, if you introduce the limit z tending to infinity on the right hand side, only the term x1 will remain. All other terms will vanish. All right. So that's how you get x1. In a similar manner, you will get x2, x3, etc.
Answer.
Hmm. Now this is the final value theorem. If xz is rational, that means a ratio of polynomials in z, or it can be z to the power minus 1, then
Sir, can you please
z
show the
minus
last
1.
expression, last expression of that
Okay,
final?
sorry.
Thank you, sir.
Sir, can you please explain again how we are writing that x1, x2 and x3?
I am explaining x1 only, all right? Others will
Yes, sir.
follow in a similar manner. What will be, if you multiply both sides of xz by z, what will happen? What will happen if you multiply both sides by z?
Sir, the z along with the x1 will get vanished and other terms will get multiplied by the z.
Just 1 minute.
Means
Z, X, Z. Sorry. Minus Z, X0. All right. That will be equal to right hand side you will have x1. All right. What other terms will be you will be having on the right hand side? x2 z to the power minus 1, x3 z to the power minus 2, like that. Just 1 minute. Just see here, zxz minus zx0 is x1 plus x2 z to the power minus 1, x3 z to the power minus 2, etc. Now here if you introduce that limit, z tending to infinity, all right, what will happen? Limit z tending to infinity, zxz minus zx0. Here if you introduce the limit z tending to infinity, what will happen? All these terms will become 0. Only x1 will be there. So x1 is limit z tending to infinity, zxz minus zx0, as I have written here. Understood?
yes sir, got it.
In a similar manner, you can derive the others. Final value theorem.
স্যার ফাইনাল ভি থিওরেমটা স্যার আরেকবার এক্সপ্লেইন করে।
ফাইনাল ভ্যালু থিওরেম তো আমি কিছু বলিনি।
ফার্স্ট যে লাইনটা স্যার এক্স জেড রেশনাল ওইটা।
If xz is rational, rational means it is the ratio of polynomials in z, and the poles of z minus 1 xz have magnitudes less than 1. This particular case will be clear to you as we proceed further. All right. Why
Okay,
am I
sir.
writing have poles of this z to the power minus 1 into xz have magnitudes less than 1? Then the final value of xn, it can be obtained simply by introducing this limit z to the z tending to infinity, z minus 1 by z xz. So it is actually, you need not write this thing, is same as limit z tending to 1, z minus 1 into xz. Because in digital control system, that type of expression is very common. That's why I have written it. But if you simply write limit z tending to 1, z minus 1 into xz, that is sufficient. That is x infinity. I may add a couple of more properties later. Let me think over it. I'll just start the mapping between S plane and Z plane, then I'll end today. FBT stands for final value theorem, remember. Mapping between S plane and Z plane. What does it imply? I want to find out the correspondence between different regions of S plane and different region of Z plane. What is the importance of this study? What's the motivation behind such discussion? The motivation is that in case of continuous time signals and systems, you have seen that the pole zero configuration, it has important bearing on the behavior of the signals as well as pole zero configuration of the Laplace transform rather of signals. They have important bearing on the nature of behavior of the signals, and pole zero configurations of transfer functions of continuous time system. They also have important bearing on the time domain behavior. Therefore, if I want to extrapolate those observations to the case of discrete time signals and systems, I must find out how does the LHS, left-hand side of the S-plane, correspond to some region in the Z-plane? How does the J omega axis in the S-plane correspond to a particular region or particular contour in the Z-plane? How does the right-hand side of the S-plane correspond to a particular region in the Z-plane, etc.? Apparently, this appears to be a very easy task because I have already thrown some light into this feature. This requires, as we will show, this will require a lot of what should I say, analysis to observe the finer details. So first write down this importance or motivation of the study. Have you written it?
Yes, sir.
That was the expression for Z in the exponential, in the polar form as well as in the Cartesian form. So from this expression, you can easily understand for sigma equal to 0, magnitude of Z is 1. Sigma equal to 0 in the S-plane corresponds to the J omega axis. So J omega axis in the S-plane maps onto, we say it maps onto the circumference of this unit circle centered at origin in the Z-plane. All right. Now, if sigma is less than 0, then what will happen? In the S-plane, it corresponds to that area, the left-hand side of the S-plane. Sigma less than 0 means magnitude of Z is less than 1. What area does magnitude of Z less than 1 represent? It is the interior of this unit circle centered at origin in the Z-plane. Similarly, when sigma is greater than 0, magnitude of Z will be, as you can see here, it's greater than 1. So that will correspond to the right-hand side of the S-plane. So right-hand side of the S-plane corresponds to the exterior of the unit circle centered at origin in the Z-plane. Now this is very simple. I have perhaps already pointed it out. But question is, one thing is sure, if you travel along the j omega axis, you will be traveling along the circumference of the unit circle centered at origin in the Z-plane. There is no doubt in that. But if I ask you the question, you start from minus omega equal to minus infinity and sweep the j omega axis, end at omega equal to plus infinity, what will happen here? Where from will you start and where from will you end? Where will you end? That is the question. If we start from the origin, then what will be the corresponding point in the Z-plane from where we will start? And if we move up and move up to infinity, where will we end here? All right, that is the question. Anyway, write this down. Next day I'll move on to.
স্যার ম্যাপিংটা একবার জানাবেন
হ্যাঁ
এই ম্যাপিং জায়গাটা একবার দেখলাম স্যার
mapping between S-plane and Z-plane. Mapping means to find the correspondence between S-plane and Z-plane. Which region of S-plane corresponds to which region of Z-plane? I have shown here that sigma equal to 0 means magnitude of Z is equal to 1. Sigma equal to 0 in the S-plane, what will it represent? The j omega axis, isn't it? Because if you travel along the j omega axis, you are traveling with sigma equal to 0. So correspondingly, because the magnitude of Z is 1, what is the locus of the points which you will travel? The circumference of this circle, isn't it? Circumference of this circle. That means we say the language that we use is that the j omega axis in the S-plane maps onto the circumference of the circle centered at origin in the Z-plane with unit radius, colloquially or loosely called the unit circle symbol. Sigma less than 0 means it corresponds to the left-hand side of the S-plane. Sigma less than 0 means you are considering points in the S-plane with negative real parts. That means you are considering points in the left half of the S-plane. So if you have any point in the left half of the S-plane, then if you sample the signal, continuous time signal is sampled, then only you move on to the Z-plane, isn't it? So corresponding to any point in the S-plane on the left-hand side, what will be the location of the point? Or what region? It will obviously be the inside of this circle. Because for sigma less than 0, where exactly will it lie will not depend only on sigma, it will also depend on omega. All right. But at least what we can say, if you have any point on the left-hand side of the S-plane, then if you uniformly sample the continuous time signal to get the discrete time signal and obtain the Z transform, then correspondingly this point will move on to interior of the circle, unit circle. That is the thing. বুঝেছো? না বুঝলে বলো। যদি left hand side একটা point থাকে, sigma is 0, sigma is less than 0 for that point. এখানে আমরা কি দেখছি? Sigma is less than 0 মানে magnitude of Z is less than 1. So That point, because it has negative real part, if you sample the continuous time signal whose Laplace transform you are studying here, you get a discrete time signal. Discrete time signal, its Laplace transform is same as Z transform. So you have this unit circle centered at origin. So
তার
if you
মানে স্যার
have, বলো,
লেফট হাফ প্লেনে থাকলে ইন্টেরিয়র সাইকেলে আর রাইট হ্যান্ড প্লেনে থাকলে এক্সটেরিয়র মানে সার্কেলের এক্সটেরিয়র, তাই তো?
হ্যাঁ
হ্যাঁ, ঠিক আছে।
এটা তো এঁকেছি অলরেডি। Next day I'll move on to finer details. I have pointed out what I will study next day. You will find, let me divulge it, you will find that if you travel along the j omega axis over a finite span, the entire unit circle will be covered in the z plane. So that has an important effect. I've written it.
Yes, sir, does.
তাহলে ঠিক আছে? Please let me know the date of the next class.
Okay, sir.
Thank you, sir.
Thank you.
Thank you.
Thank you, sir.
Thank you, sir.